Okay. Right. So last day we started chemometrics part. So under the chemometrics, just to refresh what we have done last week, I will quickly go through the slides. So we talk about the chemometrics and the chemometric techniques, what is, and also we talk about the errors. What are the possible errors, possible types of errors in the analytical chemistry, and all the precision, accuracy, all these things we already discussed. And also the statistics of repeated measurement, because normally we do repeated measurement. So we discussed what are the possible types of statistics available in repeated measurements, mean, standard deviation, and how to calculate them, and the variance, the relative standard deviation. And we talk about the difference between the sample and population. So even though it is same, it has similar meaning, but there's a difference between the sample and population. We discussed about that. And the confidence interval or the confidence limits, and also the how to find the confidence limit using t-statistics. We did some calculations, and the significant test. So that is one of the most important thing we discussed, the significant test. So we discussed how to compare the mean value with the known value using a t-statistic or t-test. There we define a null hypothesis. So that is one of the most important thing. Whenever we do the significance testing, we have to define null hypothesis. So we discuss the t-statistic and also t-test to compare two experimental mean. So earlier we discussed how we can compare the mean with the known value using t-test, and also how we can compare two experimental means using t-test. Some examples, and also we discussed paired t-test. That one, paired t-test is to compare two methods of analysis. So two ways or two analytical methods. In order to compare these two analytical methods, we discussed how to do a paired t-test. Okay, that's where we stopped. So we discussed this one, and we stopped there. I hope it is clear for you, because I have not get any email or I have not get any email asking any question. So I do hope it is clear for everybody, because those significant testing, today we will talk little bit more. Today also we will start with the significant test, but something different. And what you have learned earlier, you have to know you have to know those things when we do the lecture today, right? So F-test. Let's start with the F-test for the comparison of standard deviation. Okay, so we talked last week t-test. Using t-test, we compare mean. We compare a mean with a known value, and we compared two means, and we compared means from two different experimental methods. So that t-test is for comparison of mean. And also we have to compare the standard deviation. When we compare the standard deviation, we can get a clue or we can get an idea about the precision of the method. So when we compare standard deviation, we will use F-test, that is to compare standard deviations. So when we compare standard deviation, two types of comparison can be performed. The one is to test whether method A is more precise than method B. Suppose we have two methods, A and B. So in order to test, because we should know which method is more precise for the analysis. So in order to test that, we can perform F-test. And also the second one is to test whether methods A and B differ in their precision. To test that also, we can perform F-test, just to test whether there is a difference in the precision of method A and method B. Right? Okay. Just to test whether there's a difference, we have to perform F-test, and the difference between two sample variances is significant. Right? So we are testing whether the difference between two sample variance is significant. Sample variance is the square of standard deviation. That is how we find the sample variance. In order to test, here we are testing whether the sample variance of the two methods has a significant difference. Right? And here also, as in the t-test, at the very beginning, we define or we make an hypothesis called null hypothesis. So here also we have to have a null hypothesis. The null hypothesis here is the sigma 1 squared and sigma 2 squared are equal. That means the variance, sigma squared means the variance from the method 1 equals the variance from the method 2. Right? So that means there's no big difference between the variance of two methods. Right? So that is the null hypothesis, and the F statistic can be calculated using this equation. So F equals to standard deviation of the square of the standard deviation, that means variance of the method 1 divided by variance of the method 2. And here, when you substitute values to this equation, one thing we have to keep in our mind, this F value is always equals or greater than 1. Right? So the F value should be either equals to 1 or it should greater than 1. In order to get that way, what we have to do, the S1 or the variance of the method 1 or variance that we substitute in numerator should be always equals or higher than the variance of method 2. Right? So the S1 squared should be higher than the S2 squared. So that is how we substitute values to those two terms, because we can substitute, we can pick any method as method 1. So whenever you pick the method, always 1 with the larger number substitute to the S1. And the number of degrees of freedom of the numerator and denominator are n1 minus 1 and n2 minus 1 respectively. So numerator is the one in the top of this half, and the denominator is the bottom one in this fraction. And degree of freedom, we discussed that last week. Degree of freedom we can calculate from the number of samples minus 1, n minus 1. If there are n number of samples, degree of freedom is n minus 1. So in the method 1, the degree of freedom is n1 minus 1. In the method 2, degree of freedom is n2 minus 1. You need, we will discuss an example. You will see we need this degree of freedom when we do the calculation. Right? It will be clear for you when we discuss the example. Okay, let's move to an example. Using this question, let's discuss how we can perform a F-test. So this question says, a proposed method for the determination of COD of the wastewater was compared with the standard method. The following results were obtained. So a proposed method has been compared with the standard method here, and the mean value for both methods has been given, and the standard deviation also has been given. You see, the mean value is same for both methods, but the difference is with the standard deviation. So we can get an idea about the precision. We can compare these two standard deviations using F-test, and we can get an idea about the precision here. So what question asked? For each method, 8 determinations were made. So for both methods, number of samples were n equals 8 because there are 8 determinations. And it asks, is the precision of the proposed method significantly greater than that of the standard method? Okay, that is the important thing. The question asks whether the precision is significantly greater than that of the standard method, because you can see the standard deviation of the standard method is high, but the proposed method is relatively lower compared to the standard method. Once we see this data, what comes to our mind? By looking at this data, automatically it comes to our mind, okay, this proposed method is better than the standard method. But we cannot just simply looking at the data, we cannot tell that. We have to perform an F-test to compare the standard deviation. And by doing a F-test, we can tell whether the precision of the proposed method is significantly greater than that of the standard method. Okay, so then let's discuss how to perform the F-test. So here, this is the answer for that question. First thing, we have to decide whether the variance of the standard method is significantly greater than that of the proposed method. Right? Just before talking about the precision, we have to decide whether the variance of the standard method is significantly greater than the proposed method. So F-test should be performed. F equals the variance between the ratio of the variance between the two methods. Variance means the square of the standard deviation. So I told you earlier, always F should be greater than or equals 1. Therefore, when you substitute values, the higher number should go to the numerator. Right? So the higher here, when you think about these two values, 3.31 is higher number. Therefore, we have to substitute the 3.31 in the numerator. And the denominator, we can substitute 1.51. So those are standard deviation. Here we have to take the variance. Therefore, we have to take the square of the standard deviation. When we calculate this and when we solve this equation, for F, we will get 4.8. That is the experimental or the calculated value of F. And there's a table for the F test also. You remember for the T test we had a table. So there's a table, and I will go to the table here. That is the critical values of F, right? So this table will be provided in the exam, and here this when we take a fraction, the above value is the numerator and the below value is the denominator. The V1, this row, is the number of degrees of freedom of the numerator. These numbers are the degrees of freedom of numerator. And these numbers are the degrees of freedom of denominator. Right? That is how this table has been arranged. So I will tell why it is important. So here, using that table, we have to calculate the critical value. So the degree of freedom of the denominator is given in the left. Yeah, that is what we have discussed. And in both cases, it says each method has 8 determination. So in the numerator also the number of measurement equals 8, as well as the denominator the number of measurements equals 8. Therefore, in both cases the degree of freedom equals 7. The reason is degree of freedom equals to n minus 1. So the 7 is the degree of freedom. So when you find the critical value, you have to go to this table which contains critical value, and the numerator, the degree of freedom of numerator is 7. So we have to have a value from this column, right? And the degree of freedom of denominator is also 7. Here we go along this line until the 7th column, and this number 3.787, that is the critical value of F when the degree of freedom of numerator and denominator are 7. So for this particular question, the critical value for F is 3.787, right? And then let's move back. So the degree of freedom for the critical value of F is 3.787. Then the calculated value is 4.8. So the calculated value, that means 4.8, is greater than the critical value 3.7. So if the calculated value is higher than the critical value, what we do for the null hypothesis? We reject it. That's the same thing we did for the t-test. So because when the critical value, when the calculated value exceeds the critical value, we reject the null hypothesis. That means we say, okay, the null hypothesis is not correct. We cannot come to that conclusion. In the null hypothesis, what we define? We define that the variance or the standard deviation of both methods, there's no big difference. But because the calculated value exceeds the critical value, now we cannot say that. So the variance of the standard method is significantly greater than that of the proposed method. So that is how we come to the conclusion. So that means the proposed method is more precise than the standard method. So in the question it asks whether the precision of the proposed method is high. So after doing the conclusion also after doing the calculation, we can come to the conclusion that the proposed method has higher precision than the standard method. Okay, so that is how we perform an F test to compare two means. Okay, then let's go to the outlier. We know whatever the experiment we perform, there might be some outlier. So, for example, if you do a titration, you have to do 3 trials, and based on the values you got, you have to decide whether all are similar or whether there are any outliers. So, by simply looking at the results, we cannot tell, okay, this is an outlier. There should be more systematic way. There should be a way to determine whether there are some outliers present. So, Grubbs test, that is the significant test that we can perform to test for outliers. So, Grubbs test is the one. So, we call that G. We can call it G test also, but the name is Grubbs test. So, using this Grubbs test, we can compare the deviation of the suspect value from the sample mean with the standard deviation of the sample. So, if we have any suspicious value, whether it can be an outlier or not, we compare that suspicious value with the sample mean and standard deviation of the sample. So, this is how we perform the Grubbs test. In order to use Grubbs test for an outlier, that is to test the null hypothesis. Here also there should be a null hypothesis. So the null hypothesis is that all measurements come from the same population. So that means there are no any outlier. All are from the same population. So we assume in the null hypothesis, we hypothesize that all measurements come from the same population. So there are no any outliers. Right? And the statistic G is called. So because of that Grubbs test, we call this as G statistics. To calculate the G value, the suspect value minus mean over standard deviation. Here also note that we take the magnitude. We are not taking the sign. We only take the magnitude of the value. Right? When we take the difference, if it is a negative value, we ignore the negative sign, we take the magnitude only. And note that mean and standard deviation are calculated with the suspect value included. Right? So, because in the null hypothesis, we assume or we hypothesize that all the values or all the measurements come from the same population. Therefore, when you calculate the mean and standard deviation, for that calculation, you should include the outlier value or suspected value. We don't know whether it is an outlier yet. Therefore, we have to include that suspicious value when we calculate the mean. So that is one point that some of you get confused. So we think, okay, we are testing this value. This is a suspicious value, so we should not incorporate this value when we calculate the mean. No, we have to include that suspicious value when we calculate the mean and standard deviation. Okay, let's move and see how we can do the calculation using one example. Okay, this is an example to find an outlier. So there are some values. 4 measurements have been taken to determine nitrite concentration in a river water sample. And the question asks, the last measurement is noticeably lower than the others and is thus suspect. So the last measurement, 0.380, it is less than the other 3 measurements. Therefore, it is a suspicious value. The question asks, should it be rejected? Okay, so So we have to perform a G test, G statistic to see whether this 0.380 is an outlier or not. So the first thing, you have to calculate the standard deviation and mean. So when you calculate the mean and standard deviation, you have to take all 4 measurements, including 0.38. And the 4 values have mean of 0.3985, that is the mean of the all 4, and standard deviation is this. Then we can substitute this mean and standard deviation to G equation to calculate the G statistic. So the G statistic equals the magnitude of suspect value minus mean over standard deviation. So suspicious value is 0.38. 0.38 minus mean is 0.3985. So you see, when we take the difference, the value has negative sign, but here we take only the magnitude. Therefore, we ignore the negative sign, and when we divide it by the standard deviation, we will end up with this answer, 1.432. That is the G statistic for the, that is the calculated G statistic, right? And there's another, again there's a table, this table has critical values of G. So using this table, we can calculate the critical value for that measurement. So here, how many measurements? There are 4 measurements. Therefore, since there are 4 measurements, the sample size is 4. Here, the sample size is 4. So we have to find the critical value which is correspond to sample size 4. It is 1.481. Then compare that critical value with the calculated value. So the calculated value is 1.432 and the critical value is 1.481. So the calculated value is less than the critical value. Because this calculated value is less than the critical value, we can say the suspect measurement should be retained. We cannot reject the suspicious measurement. So it is not an outlier. So we have to keep this measurement in our calculation, right? So that is how we determine whether this 0.38 is an outlier or not. Okay. Okay. Then let's see. Here in the question that we discussed earlier, there were 4 measurements. So the number of measurement was 4. Now, for the same measurement, it has been added another 3 new measurements. So all other 4 are same, but here we have been added another new 3 measurements. And then again question asks, now okay, there are 7 measurements now. Now should the value of 0.38 still be retained? The question asked because the number of measurements has been increased, and again those values also closer to 0.4, and now also they ask still should we retain this 0.38. Again we have to calculate the mean for these 7 values and the standard deviation for all 7 measurements. Then after finding mean and standard deviation, we have to calculate the G statistic for these 7 measurements. So the suspicious value is 0.38, mean is 0.4021, and divide this by standard deviation. So again, this value is a negative value, but we take only the magnitude, and for the G, we get 2.031. Now, we need the G table. So here the number of samples are 7. There are 7 samples. So the sample size is 7. Then go to G table. To 7, the critical G value is 2.02. Right? So for sample size 7, the critical value is 2.02. Now see, the 2.02 is smaller than the 2.031. That means the calculated value is greater than the critical value. When the calculated value is greater than the critical value, now we cannot keep the null hypothesis. We should reject the null hypothesis. Right? So the null hypothesis means we hypothesize at the very beginning all measurements are from same population. That means there are no any outliers. So here we keep the null hypothesis, and that means here we cannot keep the null hypothesis because the sample size, when the sample size is 7, the calculated G value was higher than the critical value. Therefore, we should reject the null hypothesis. Right? But the earlier case, the calculated G value is smaller than the critical G. That's why we keep the null hypothesis in the previous case. Here, we cannot keep the null hypothesis, we reject it. Therefore, we can conclude that, okay, this 0.380, this value is an outlier. We cannot keep this value. It is an outlier. So, we reject or we remove that value. Is that clear? So, I think it is easy in statistical testing. It is same thing. We do the calculation. Only thing we have to remember, or we have to know which test should I apply for this particular incident, and then how to calculate the value. So we have to keep in mind, we have to memorize the equation, and then we do the calculation, and then we compare with the critical value table. If the calculated value is less than the critical value, we keep the hypothesis. If the calculated value is greater than the critical value, we reject the null hypothesis. It's simply the same thing we have to do. Right? Okay, so that is for outlier testing using G statistic. And there's another test called Q test or Dixon's test. This one we apply for small samples. The G test we can apply for larger samples. When there are large number of samples, we can do G test. But if there are small number of samples, we can do Q test or Dixon's test. Normally, this Dixon's test can be performed when the sample size is in between 3 to 7. And in order to use the Dixon's test for an outlier, that is to test the null hypothesis. So here the null hypothesis again, all measurements come from the same population. So that is the null hypothesis. That means there are no any outlier. All are from same population. There's no any outlier. And the Q. Here it is easy to calculate Q. We have to take the magnitude of suspected value minus nearest value and divide that number by the difference between the largest and the smallest value. So that is the equation we have to use to calculate the Q statistics. Again, same data set. earlier we used this 7 data set. And again, let's do the Q test and see whether this number is an outlier or not. Okay, here using the Q test, when we apply the suspect, here the suspect value is 0.38 minus 0.4, that is the nearest value, and the largest value using this number is 0.413, and the smallest value again 0.38. When you solve this, we will get 0.607, 606. Right? And then there's again, let's go to, there's a table for Q statistics. Here's the table, and the sample size is 7. When the sample size is 7, the critical value is 0.568. That is the critical value when the sample size is 7. Now, when the sample, here instead of 0.568, it has been written as 0.57, but you please don't round it as 0.57, use 0.568. And here for the sample size is 7, the critical value should be 0.568. Therefore, the calculated Q is higher than the critical value. When the calculated Q is higher than the critical value, we reject the null hypothesis. So the suspect value 0.380 is thus rejected. So again, from the Q test also, we got that the same answer. So this 0.380 should be rejected. In the earlier also, when there are 7 number of measurements using G statistic, we got the answer that okay, this 0.380 is an outlier. Even with the Q test, you got the answer that this 0.380 is an outlier. So you see, using both tests, we will get a same answer when the sample size is small, right? The only difference between G and Q test is G test can be applied to determine an outlier from a larger number of samples, but the Q test can be applied only for small number of samples. Normally, when the sample size is between 3 to 7. Okay, so that is the most important and readily using statistical test or the significant test. So if you have any question, please let me know, and I'll try my best to answer within this time period, but if not, please email me. And also I will give you a tutorial because we have lectures only next week. After next week, on 14th of Monday, I will take another lecture from 2 to 3, and then we will do a tutorial. Even for the tutorial also, I prefer, it would be better if you come, if you are physically available, but it's okay even though even you are not physically available. Let's do an online tutorial and some revision. Okay. And analysis of variance, that's another new section. So I think so far it is really it's clear and really basic statistical things, and from next onward, after the analysis of variance and again the chemometrics, the multivariate analysis comes to the picture. So that part is little bit difficult, the multivariate analysis, but I will try to make it simple as much as possible. Okay. Okay. Analysis of variance. Variance means the standard square of the standard deviation, the sigma square, or if it is a small sample, it is S squared. We can abbreviate this analysis of variance as ANOVA. You will hear, when you do the analytical chemistry, you will hear this ANOVA, that word most often. So let's discuss how to do this analysis of variance. Okay. No. So far we discussed that the whether mean with some, whether there's a difference between a mean and some critical value, or whether there are some difference between two means. That's what we discussed so far. But in real analytical experiment, if we take a real analytical experiment, most often there are more than two means, right? So therefore, we have to compare more than two means. With the method that we have discussed so far, we can compare only two means. But there should be a way to compare more than two means. In that case, ANOVA comes to the picture. So using the ANOVA, we can compare more than two means. For example, let's here some examples that we have to compare more than two means have been listed. So when, for example, when we take the mean concentration of solutions stored under different conditions. So suppose we store a single solution. Single solution means, let's say, sodium chloride solution. We store it in different conditions. Or suppose a protein solution, it is highly temperature sensitive. So if we store that protein solution in high temperature, in low temperature, or at room temperature, then their behavior will be different. So, and if we compare the means, if we, let's say we quantify the number of proteins present, and when we quantify the number of proteins present, we have to compare, we have to take the mean value and we have to compare the means of all these three. So those means will be different, and we have to compare several means in that case. And another example is mean concentration of same analyte in different methods. So suppose we are doing this, we are analyzing the same analyte but using different method. We have 5 different methods. So in that case, we have 5 different mean values. We have to compare these mean values, whether all are same or whether there's a difference, right? So those are some examples that we have to compare more than two means. Actually, in real analytical experiment, you have to compare more than two means in most of. So, in the analysis, when we analyze more than two means, two possible sources of variation. There are two possible sources. So, there may be some random errors. The random errors, it is really difficult for us to avoid. So, all of the time, random errors are possible. And also, controlled or fixed effect factor. What does that mean? For example, solution storing condition, analysis method or analyst. Those things we cannot change. It is a fixed. So the analyst we cannot change. So if suppose we are comparing some analytical methods, so that method we cannot change. And if we store the solutions in 3 different conditions, we cannot change the effect coming from those conditions. So the sample to sample, when we store in different conditions, the values or the real measurement we got from sample to sample can be changed because of that storage condition. That is a fixed value or fixed error. We call it as controlled or fixed effect factor. So these two possible sources of variations are possible. And this using the ANOVA, it can be used to separate and estimate the different causes of variation, whether the variation is due to control factor or whether it's due to random error. So using this ANOVA, we can determine whether it is a random error or whether it is a controlled or fixed effect factor. Right? So that is the importance of this ANOVA. And here I think it would be better here also how to do this analysis. Let's discuss this using a simple example. So it will be easier for you to understand when we discuss it using an example. Okay, so I told you that the main importance or main advantage of this ANOVA is we can compare several means using this method. So ANOVA test whether the difference between the sample means is too great to be explained by the random error. What does that mean? So if using this calculation, if we got okay, there's a significant difference, that means the difference is more due to fixed or controlled error. So using this ANOVA test, we can determine whether there's a difference between the sample means and also whether if there's a significant difference between the sample mean, so the error is too great, it is high. So it is not just because of the random error, that error is due to fixed effect error. Okay, let's take this example. Okay, there's a table. This table have results obtained in an investigation into stability of fluorescent reagents stored under different conditions. Right? So here we are testing fluorescence reagent. So using the spectrophlorimeter, we do the analysis. So here 4 different conditions. This fluorescent reagent has been stored in 4 different conditions. The first one, we freshly prepare the solution, the reagent. Freshly prepare the reagent and immediately take the measurement. That is the very first one. And the second one, after preparing the solution, we store that solution in dark place for 1 hour. What is happening when we store in the dark place? There's no any interaction between light. Therefore, still we can keep the fluorescent reagent active. And in the third one, the reagent has been stored for 1 hour in subdued light. So there are certain amount of light and still it has been stored for 1 hour under a subdued light. And the final sample, the solution, store for 1 hour in bright light. So the light intensity is higher here, and again it has been stored under this bright light for 1 hour. So this fluorescent dye interact with light in different way. So when the fluorescent dye, you know, when the fluorescent reagent interact with light, this fluorophore get decayed. Therefore, the fluorescent intensity will be less with the time. And then the same reagent under 4 different conditions, we take the fluorescence measurement. So how many replicates? They have performed 3 replicates for each condition. So the number of replicates for each condition is 3. And here the third column shows the mean value for 4 different conditions. And also the overall mean has been calculated. This data, we need this data. I will show you using this how we perform the ANOVA test, right? So that is the experimental data we got. Now let's move to the calculation. Before that, I would like to explain something. So here also, as we did for T statistics, G statistics and Q statistics, we need to define a null hypothesis. Okay, so the null hypothesis is all the samples are drawn from a population with mean and mu and variance sigma naught square. So here all 4 samples, we come to that hypothesis. That is what we test. What is the hypothesis? All 4 samples here, even though the storage condition is different, the reagent is same, right? So what we hypothesize, all 4 samples comes from a same population. So the population mean is mu and the variance is sigma square. So that means there's no big difference between the sample means, right? Suppose if all the solutions come from same population, it cannot be difference in the mean. So we have to assume, okay, all samples come from same population and there's no big difference between means. That is the null hypothesis, right? And this variance for sigma naught squared can be estimated in 2 ways. Variation within the samples, variation between samples. So what does that mean? Here, within the sample, let's take the sample A. We have performed 3 replicate measurements. When we perform 3 replicate, the variation can happen. So that variation we call as the variation within the sample, right? So the same sample, we take replicate measurement. So that variation we call variation within the sample. And the second one is variation between the sample. So here there are 4 methods, there are 4 conditions. For every 4 conditions, we can get 4 different means. And we can compare these mean also. We can compare these 4 values, 4 mean values. So that variation, when we compare that, we still can get some variance. So that is the variation between sample. So name also implies what it means. So that is the variation between sample. Okay. And then we have to calculate the variation within sample and variation between sample. Now let's discuss how to do that calculation. So the first one is variation within sample. So variation within sample means we have to compare the values or the measurements in each condition. So in that case, we need the standard deviation and the variance. So standard deviation, the same thing we had done earlier. So we did the calculation for standard deviation. And since again here, the degrees of freedom is n-1 because it is a relatively small number. S is for sample, when there's a S, when we calculate S, we should have n minus 1. Suppose we are calculating population standard deviation. When it is population standard deviation, instead of S, we have to have sigma. And here, instead of n minus 1, we take n, number of measurement. It's because of the population. Here, in population, we have large number of samples. We discussed that in detail last week. And also you need variance. Variance is the square of the standard deviation, S square. Okay? And for each sample, a variance can be calculated by using this formula. So this is for standard deviation. The variance is standard deviation, the square of the standard deviation. When we take the square of this, we can remove the square root and then it becomes this equation. So using this equation, we can calculate the sample variance. Right? And here, let's go to sample A. I will move back to the table. In the sample A, mean is 101. And the replicate measurement we got 102, 100 and 101. So those are the measurement. Those are the xi value and this is the mean. Now we substitute those values here. So 102 minus mean, 100 minus mean, 101 minus mean. Then we take the square of the difference in all cases, and n minus 1 is the degrees of freedom because number of samples is 3 minus 1. Then when we solve this equation, we will get the variance of sample A equals 1. And similarly, we can calculate the variance of sample B. When we calculate the variance of sample B, we will get 3. That is the value. And in the same way, we can calculate the variance of sample C and D. In those cases, the variance of sample C equals 4 and the variance of sample D is also 4. And within the sample estimate, so within the sample here, the variance within the sample, we can add all these 4 values and take the mean, right? Take the mean. Simply here we get the mean. So we add 1, 3, 4 and 4, and since there are 4 variances, we divide this number by 4. Then within sample estimate, within sample variance, we get 3. So that is the sigma naught square for within sample measurement. I hope it's clear. And then degrees of freedom. So when it comes to the degrees of freedom, how to calculate the degrees of freedom? So in each measurement, I'll go back to the table here. The number of measurement is 3. There are 3 number of measurements. Therefore, when we calculate the degree of freedom, it will be 2. 3 minus 1. Since there are 4 means, there are 4 conditions. We have to multiply n minus 1 by 4. So when we multiply n minus 1 by 4, we will get 8 degrees of freedom. We need this when we do the calculation. That's why I am showing you how to find it. So here within sample, for the within sample variance, the degrees of freedom is 8. Right? I think it will be little confusing for you because this ANOVA test, what I will do, I will first explain one by one. Again, I come back to the first slide and go through the slide, then you will understand it better. Okay? Alright, so we calculate within sample estimate of sigma naught squared. So that is 3 and the degrees of freedom is 8. And this variance value is known as mean square. This value, there's a special terminology we use. We call it as mean square. Right? And the reason for telling it as mean square is this value involves the sum of squared terms divided by the number of degrees of freedom. So when we calculate this sigma naught value, I'll go back to the previous slide. So here we take the square term here. We take the square term and divide it by the number of degrees of freedom. That means we are taking the mean of a square term. We are taking a mean of a square term. That's why we call this variance as the mean square. Here we call it as mean square. Right? And again, I'm telling you degree of freedom is 8, mean squared is 3. So this is how to calculate the variance within sample. I told you at the very beginning, when we do the ANOVA, we have to calculate the variance within sample as well as variance between sample. So we already discussed how to calculate the variance within sample. Now let's move to variance between sample. How we can calculate the variance between sample. Before I move to this part, any of you have any question? Is it clear so far? I hope it's clear because nobody asked me any question, so I think it's clear. But if you have any question, because I tried to make this simply as much as possible. So if you have any question, please let me know. Okay. Okay. Now let's see how to calculate the variation between sample. So remember, still we are in ANOVA calculation, so I have not tell anything. Yeah, I have one question, one request actually. It is not a question, one request to upload past papers questions to LMS. Actually, I think this is a new course, so there's no any past paper question, but there's another course unit for special degree level 2, I think. I will ask Dr. Kirti, so he will upload these past papers to LMS, right? And what I am telling you, so I will upload a tutorial. So that tutorial will cover all these statistics. That tutorial, still I am preparing that tutorial, so most probably after our next class, what I am planning after the 30th, next Monday, we have the lecture. After that lecture, I will work on that tutorial and I will cover all the questions which have been taught in the class, and then we will discuss that tutorial on 14th of December, right? So, and that tutorial will be, yes, I know you can get an idea about what the exam questions will be and what it should be looks like based on the past paper question also, but this course is new, therefore I think the tutorial will be more helpful for you. I will upload that tutorial and I'll let you know when the tutorial is ready, but keep in mind that 14th of December from 2 to 3 we will discuss that tutorial. Okay, right. Okay, then let's move to the sample between variation. So if a sample is taken from, let's say we are taking samples. When we take samples, if it is taken from the population with variance sigma naught square, this sample between variation, this part is little confusing. Please pay attention to what I am telling, right? So suppose we are taking samples from a population. That population has variance sigma naught square. Then their means come from population with variance sigma naught square divided by n. That is sampling distribution of the mean. What does this mean? If I simply telling this, okay, now there's a population, and in that population we are collecting samples from population. When we collect samples from that population, the variance is simply sigma square, right? And suppose you are taking means from the population. You are taking means, not the sample. You are taking sample mean. When you take in the sample mean, instead of sigma square, you should take the mean of the sigma square, right? So that's clear. When you take the sample, it is simply the sigma square. And when you take the sample mean, you should take the mean of the variance. That is sigma square divided by n. And that is the population mean, right? When there are large number of samples, we take the sigma value. We represent the variance as sigma. But normally when we take 2-3 samples, instead of sigma, we replace it by S or standard deviation. The same thing here, when we go to the sample from the population, when we go to the sample, when we calculate the mean, instead of n, we use n minus 1 instead of n. That's what we have discussed. So the sample mean variance, that is the population mean variance, sigma squared over n, that is the population mean variance. When it comes to the sample mean variance, so instead of this sigma, substitute this sigma by S, and instead of n, we substitute by n minus 1. This is the sample mean variance, right? So all 3 words are important. Sample mean variance. Then we calculate the sample mean variance. Here in that question, when we calculate the sample mean variance, I will go back to the table. this table. So here, when we go back to this table, what we have to do, the mean, we have to compare this mean. Now we are calculating the variance between samples, okay? We are calculating the variance between samples. So when we calculate the variance between samples, we compare this mean, the mean of A, mean in the condition A with the overall mean, and mean of the condition B with the overall mean, C with the overall, D with the overall, right? So here, that is how earlier, when it is when we calculate the variance within sample, what we have done, we calculate each replicate with their mean. That is what we did in the variance within sample calculation. Now we are calculate the variance between sample. Here we calculate the mean of the each condition with the overall mean. I suppose it's clear, right? And again, I will go back to that slide. Okay, here. Now the overall mean, you see, overall mean is 98. That is the overall mean. And the mean for the method A or condition A is 101. Mean for the condition B is 102. Condition C mean is 97. Condition D mean is 92. So when we calculate the variance, we have to take the difference between the overall mean and the mean of the individual condition. Right? And then the degrees of freedom. There are 4 measurements, 4 conditions. So 4 minus 1. Then the sample mean variance. The sample mean variance is 62 over 3. We will not solve this part. I will tell why. We are solving the numerator. The values of numerator will get 62. The denominator will get 3. We are not solving this. We will keep this. And S0 squared divided by n minus 1. That is the sample mean variance. That is equals to 62 over 3. Right? Now, here I replace this S0 from the variance because we are normally here we talk about the population. That's why I replace this from the sigma naught squared. And then the n minus 1. N is 4, therefore the n minus 1. There are 4 measurements, so the n minus 1 becomes 3. Then these 3 will cancel and the sigma squared will become 62. Right? Here the degrees of freedom is 3. In the earlier case, degrees of freedom is 8. The reason here there are 4 sample means. Therefore, degree of freedom is 3. There are 4 sample means. That's why degrees of freedom is 3. Right? And again, this sigma naught square here also known as the mean square. Mean square is 62. And the degrees of freedom is 3. That is the sample variation. That's the between sample variation. This is called between sample variation. And if we summarize the data, if we summarize the values we got, within sample mean square or within sample variance, we got 3 with 8 degrees of freedom, and between sample mean square, we got 62 with 3 degrees of freedom. Now, we are going to calculate, or we are going to test whether there's a big difference between this sigma value. Now something should come to your mind. So earlier, this is like, this variance is like standard deviation, the square of the standard deviation, right? So sigma naught squared means the square of the standard deviation or variance. Earlier we did one test. If you remember, we discussed it today. We compared two standard deviations. When we compare two standard deviations, we used F-test. Here we can, here also we can calculate or we can compare these two variances with the F-test. Right? Let's go and see what we can do. And again, we are going to perform a test. So we need to have a null hypothesis. So the null hypothesis means these two estimates of sigma squared should not differ significantly. So the variance within sample and variance between sample should not differ significantly, or there should not be significant difference with the variance within sample and variance between sample. So, and if the null hypothesis is incorrect, the between sample estimate of sigma squared will be greater than the within sample estimate because of the between sample variation. So, if the null hypothesis, if we using F-test, if we confirm, okay, the null hypothesis is not correct, it is wrong, that means the between sample estimate is higher compared to the within sample estimate. And these mean values have significant difference. That means these all values are not coming from the same population. We cannot tell those are from the same population. And we can make a conclusion, okay, this sample variation is different. That means the storage condition is highly affecting. We can come to that conclusion also, right? So now let's see how we can test this hypothesis. So that hypothesis to test whether between sample variance is significantly greater than the within sample variance, we perform a F-test. So F-test, we learned this one earlier, that is the variance of the method 1 over method 2. I told you, whenever you perform F-test, always the numerator should get the higher number, higher value, because the F should be either equals to 1 or greater than 1. Now, within sample variance equals 3 with 8 degrees of freedom. And between sample variance equals 62 with 3 degrees of freedom. That is what we calculate. Now we substitute those variance values to here. So in order to satisfy that condition f should be greater than or equals 1, instead of S1, I will substitute 62 between sample variation. And instead of S2, I'll substitute within sample variance 3. When we substitute those two, F equals 62 divided by 3. So when it comes to 62 divided by 3, it will be 20.7. Now, you remember we required this degrees of freedom. When we go to the F statistic table, we need the degrees of freedoms to calculate the critical value. That's why I calculate the numerator, and that's why I calculate the degrees of freedom for the within sample and between sample variance. So in the numerator, the degree of freedom is 3 and denominator degrees of freedom is 8. I'll go back to F-test table just to show you here. Numerator degree of freedom is 3. So here, and denominator degrees of freedom is 8. So we should get this number. Right? 4.662. From the F-test table, now critical value is 4.066. Now, the critical value of F, is it higher or lower than the calculated value? So, the calculated value is higher than the critical value. Calculated value is 20.7. So, the calculated value is higher than the critical value. That means null hypothesis is rejected because the calculated value is high. Therefore, we cannot keep the null hypothesis. So, we reject the null hypothesis. And that suggests that the sample means significantly different. So, the sample means is the overall, there are 4 samples. So, the between sample measurement is significantly different. So, it is not from the same population. So, it is significantly different. So, here in this example, we compare 4 sample means using the ANOVA. We compared 4 sample means and determined whether the sample means are significantly different or not. This is how to do the calculation for the ANOVA. I will again go back to the first slide and quickly go through what we have done. Then now you know the overall picture. Now you know how to do the calculation. As a revision, I will go back to the first ANOVA slide and explain you. Let's see. Here, I'm repeating the same thing. So this one we don't need. So here, this is the mean values that we have to compare. So we have 4 conditions, 4 different means, and then we have overall mean. The first thing we have to do is determine the within sample variation. When we determine the within sample variation, we have to take the difference between each measurement with each mean for every condition. So we are comparing the mean of the single condition within the every measurement. So that is what within sample variation. So using the within sample variation, we got sigma squared as 3, and there are 4 means, and each one has 2 degrees of freedom because there are 3 replicates. So 3 minus 1 equals 2, and there are 4 conditions. We multiply that 2 by 4. We will get the 8 as the degrees of freedom. Then we calculate the between sample variation. So when it comes to the between sample variation, so we are comparing mean value from every condition with the overall mean. So here we are not taking individual measurement. We are not considering individual measurement. We are considering each and every mean value. So mean value from each condition, we compare it with the overall mean. And then we find the degrees of freedom as well as the variance. So from these methods, we calculate the within sample variance and between sample variance, and we have to find the degrees of freedom. After we find it, we will test whether there is a significant difference between these calculated between these mean values using F-test. So we perform as F-test. So using the F-test, if the calculated value is greater than the critical value, we reject the null hypothesis. And if the calculated value is less than the critical value, we keep the null hypothesis. That is how we made conclusion in the ANOVA. I will give you another example for this one, then the answer as well, so it will be more clear. Okay. Right, and also I am covering the Millers and Miller textbook. Please read that one because by reading that book, it will be more helpful. The questions also I am discussing are from that book. So it will be useful for you to understand this more clearly. And then, so we discussed ANOVA just to compare several means. Then let's move to chi-square test. This is another test, chi-square test. So here, we test whether the observed frequencies agreed with those expected according to some null hypothesis. So the observed frequency value and the expected value, that is the equation. I will show the example and show you how to use this chi-square test. So this is the equation. Observed, the difference between observed and expected frequencies over expected frequency. Here, we are not taking a single measurement. Sorry. This is not a mean or anything. We compare frequencies. Means how often. Again, let's use this question to get an idea about the chi-squared. So the number of glassware breakage reported by 4 laboratory workers over a given period are shown below. Is there any evidence that the workers differ in their reliability? Okay. So the question asks, people are breaking glasswares. So based on the frequency of the breaking glassware, whether we can tell whether these workers are reliable or not. This is the number of breakages from 4 labs. So, the null hypothesis is, first thing we have to define a null hypothesis. There is no difference in reliability. So, it is reliable. Workers are reliable. That's the null hypothesis. So, assuming that the workers use the laboratory for an equal length of time, we would expect the same number of breakage from every. The total number of breakage is 61. There are 4 workers. When we divide 61 by 4, it becomes 15.25. But actually, we cannot break 15.25 because we cannot break 0.25 number of glassware. But since it is a calculation, we can use that 15.25 as the expected value. In the chi-squared equation, as the expected value, we can use this 15.25. Right? So, here, these are the numbers 24, 17, 11 and 9. And the expected frequency is 15.25. Then, the observed and expected, the difference between observed and expected frequency. 24 minus 15.25 becomes this. Then we can calculate those differences. And then we can calculate the square term and divide by the e-value again. So we will end up with this number. And the chi-squared value equals the summation of all 4 numbers. Right? So that is the chi-squared value. And one thing here, here again, there will be a table, chi-squared table. This is the table. This table contains the critical values of chi-square. Here also we should have the number of degrees of freedom. And the number of degrees of freedom. Here, how many number of degrees of freedom? There are 4 different labs. Then n becomes 4. Then number of degrees of freedom will be n minus 1. That means 3. Okay. So for the 3, the critical value is 7.81. That is the critical value for 3 degrees of freedom. 7.81. Then the calculated value for chi-squared is 8.96. The 8.96 is greater than the critical value because the critical value is 7.8. So the calculated value is greater than the critical value. Since the calculated value is greater than the critical value, then we reject the null hypothesis. So at the very beginning we hypothesized that okay, there's no difference in the reliability of workers. Workers are reliable. That's what we made. Now, using the chi-squared value, we cannot keep that null hypothesis. We have to reject the null hypothesis. That means we cannot conclude that the workers are reliable because they are breaking glasswares in different way, and that is not the expected values. So we cannot tell that the workers are reliable, and because of this chi-squared value is greater than the critical value, we have to reject the null hypothesis. So there is an evidence that the workers differ in their reliability. Okay, that is how we compare the frequencies using the chi-square. Is that clear? So we talk about the ANOVA, we talk about the chi-square, we talk about the F-test and G-test, and also Q-test. That's what we have discussed today, and I hope it's clear. So if you have any question, please let me know. You can email me. And next we have to do the multivariate analysis. So that one actually it's involves some software, but I am not going to talk about this software, and I will not teach you about that software. But instead of teaching the software, I will give you the basic idea about the multivariate analysis. That is actually one of the most important section under the statistics and chemometry. So I hope today, because we have to start that section freshly, I will cover that part on next Monday. So let's start with the multivariate analysis and the univariate analysis on next Monday. And also you will have, when you come to the university, you will have a laboratory under this course unit. So in the lab also, let's practice some of this statistical testing method and some chemometric parts. Okay, so I think it would be better to stop from here and start next day. So if you have any question, please let me know. I don't know whether it's too fast, but if I am too fast, you can ask me to slow down also while doing the lecture. But I think none of you may tell me anything about the speed. Therefore, I think the pace or the speed is not a problem to you all. Okay. Okay, then let's stop for today, and then let's meet again next Monday. All right, have a good evening.